Welcome back to the deep dive. You know, for years now, many of us, especially developers, we've gotten used to AI tools, right? Your code assistants, the co-pilots baked into IDEs, maybe simple chatbots. We're kind of comfortable with AI as a utility.
Yeah, something that helps you out.
Exactly.
Huh.
But there's this really massive shift happening right now, deep in the enterprise world. We're moving, and pretty decisively, from just using AI to actually developing and rolling out full-scale custom applications that are powered by large language models.
And that change from user to builder, that's where everything gets more complex. Suddenly you're juggling data orchestration, resource management, making sure it scales, benchmarking
It
performance.
sounds overwhelming.
It can seem like it at first glance, yeah. A big generative AI app looks complicated, but honestly, the whole thing from that initial user query all the way to the final answer the AI spits out, you can actually break it down. It follows a surprisingly predictable set of fundamental patterns and architectural layers.
Okay, so that's our mission today then, to kind of give everyone the blueprint for this.
That's the plan. We want to give you that structural understanding, cut through some of the noise around it.
All right. So our goal for this deep dive is pretty clear. We're going to unpack the typical architecture, the anatomy of an LLM application. We'll detail the three main implementation patterns, starting simple with prompting, then getting into RAG and those autonomous agents.
And then we'll trace that whole developer journey, the MLOps side of things.
Right, from idea to production. And then, crucially, show you how this tech is tackling some really tough, real-world enterprise problems. We're talking modernizing old COBOL systems and automating complex contract analysis.
Yeah, two massive headaches Gen I is actually helping with.
So this should be a shortcut to really understanding how Gen AI development works structurally. Let's start with that standard anatomy. If a developer is staring at a blank screen wanting to build, say, an enterprise chatbot, what are the key layers they need to think about in order?
Okay, yeah. We can usually break it down into four main components. They operate in a pretty clear sequence, starting right from the user screen all the way to the servers running the model. It looks simple, but this sequence, it's basically the foundation you can't skip.
All right, give us the breakdown step by step.
So it kicks off naturally with the user interface, the UI. That's the entry point. Could be a web page, an internal tool, maybe a desktop app. It's just where the user types their question or makes their request, like, summarize this document.
Okay, simple enough. But that UI doesn't talk straight to the AI model, right?
No, exactly. It passes that request to the second component, which is really important, the library or framework.
The framework, so like an intermediary. What's its main job? Why have that layer instead of just firing the request off?
The framework is kind of the brains of the operation, the logic layer. Its job is abstraction, orchestration, getting things ready. It handles all the complexity behind the scenes. Maybe it manages conversation history or figures out which specific model to call if you have several, or, like we'll discuss later, retrieves external information.
Ah, okay. So it might be deciding if it needs extra data for this question.
Precisely. Or it might be assembling the system instructions we'll talk about. It could be an open source library people use, like LangChain, or maybe a cloud provider's own toolkit, their SDK, or even a custom-built service. It manages the whole flow before the request even goes out to the big model.
Got it. So the framework orchestrates, prepares the package, makes sure it's all lined up correctly.
Yeah. And then that framework needs a way to actually send the prepared request out. That brings us to number 3, the API, the application programming interface.
The communication channel.
Right. It's the standard way systems talk. It handles things like authentication, making sure the request is formatted correctly, usually in a structure like JSON, and just sending that information efficiently.
Okay, UI to framework. Framework uses the API.
And finally, that API sends the fully prepped request to the fourth piece, the LLM provider. This is the entity. Could be a big cloud vendor, could be your own internal setup if you're self-hosting, that actually runs the large language model. They take the input, process it, and generate the response.
UI, framework, API, provider. Okay, that sequence makes sense. It grounds the architecture. Now let's shift from architecture to how you implement the interaction, starting with the most basic way. Basic prompting, just a simple API call, usually.
It really is the most fundamental pattern. It sets up that core way of talking to the model. And yeah, it's typically done with just a straightforward API call or using the provider's SDK, their toolkit. The workflow seems simple. The user's question gets put directly into something we call the prompt.
Right, but the prompt isn't just the question, is it? The quality of the answer, and maybe more importantly, making sure the model behaves itself, that depends heavily on how you structure that prompt.
Absolutely critical distinction, yeah. The full prompt, structurally, has two key parts. First, obviously, is the actual user question or the task they want done.
Okay.
But second, and this is where developers spend a lot of time tuning, is a specific set of system instructions or directives for the LLM.
Ah, the instructions. These are like the rules.
Yeah.
They control the model's personality, its limits, what kind of things go in there.
They're essentially the guardrails, the safety instructions. They tell the model how it should behave. Things like, you are a helpful assistant, keep your answers concise, or maintain a strictly professional and neutral tone. Or really important ones like, do not invent facts. If you don't know the answer, say the information isn't available.
So preventing hallucinations and keeping it on brand.
Exactly. These meta-instructions keep the model within its defined limits, protect the company's reputation, and cut down risks like making things up. Once you've got that whole package assembled, the behavioral rules, plus the user's question, that complete prompt gets sent off to the model to generate the final answer. It's simple conceptually, but it's the absolute bedrock. All the more advanced patterns build on this.
Yeah, and what's really interesting is how fast developers needed to move beyond just that basic setup. Basic prompting is fine for, general questions, but it hits a wall pretty quickly if you need answers grounded in your company's specific private data, or if you need to automate something that takes multiple steps, maybe using external tools.
Right, the model only knows its training data, which is usually a public and potentially outdated.
Exactly, and that need for specific knowledge or multi-step automation is what drives developers towards the two more advanced patterns we see everywhere now, Retrieval-Augmented Generation, or RA, and these autonomous AI agents. Okay, RAG. This seems to have become the go-to method for connecting a general LLM to a company's own knowledge base, internal documents, manuals, private research, whatever. The idea is to get specific, current answers without having to fully retrain the base model, which is expensive and slow.
That's the core purpose, specificity and freshness without touching the underlying model weights.
So how does RAG fundamentally change that request workflow compared to just sending the prompt directly?
It completely flips the retrieval part. In basic prompting, your text question goes more or less straight to the model. With RAG, the user's question first goes through a mathematical transformation. It gets converted into a numerical representation, a vector, called an embedding.
An embedding. Okay, so you turn the question's meaning into numbers, like coordinates in some high-dimensional space. It represents the intent.
Precisely. It captures the semantic essence. Then that vector is used to search a very specialized kind of database, a vector database.
Ah, okay. And this database isn't just a normal database.
No, it's been preloaded and indexed with all your company's external context. Your documents, PDFs, research papers, website content, everything already converted into its vector embedding. The search uses something like nearest neighbor search to find the chunks of text whose vectors are mathematically closest to the vector of the question.
So it finds the most relevant snippets from your documents based on meaning, not just keywords.
Exactly. These are your relevant context pieces, often called the top relevant results or hits. It pulls back those specific text chunks.
Okay, so the database finds relevant text, then what?
Only then do you actually build the final prompt that goes to the LM. And this prompt is now much richer. It contains the original user question, sure, and those system instructions for behavior we talked about, plus all that retrieved external context, those relevant text snippets.
Wow, so you're stuffing the prompt with relevant facts.
Yes. And you explicitly tell the LLM in the prompt, answer the user's question based only on the provided context. It's this dynamic, just-in-time augmentation step. It forces the model to ground its answer in your specific, up-to-date internal documents, leading to much more precise and relevant responses.
That makes sense. But it sounds like there's a big setup hurdle there. You mentioned the vector database has to be preloaded.
Yes, absolutely. That's the crucial prerequisite. The data ingestion pipeline. RAG needs significant upfront work. You have to get all that domain-specific knowledge ready. This means breaking down your documents into manageable chunks, cleaning the text, converting every single chunk into its vector embedding using an embedding model, and then storing those vectors along with metadata about where they came from in that vector database.
So if that pipeline for getting data into the vector store is unreliable, the whole RAG process falls apart.
Completely. If the context isn't there or isn't fresh, RAG can't retrieve it. That's why RAG implementations almost always rely on a dedicated framework or library to handle this complexity, the chunking, embedding, storing, and then the retrieval logic.
Okay, that clarifies RAG. Now let's move to the third pattern, the really advanced one, AI agents. This is where the LLM isn't just answering questions anymore. It's actively planning and doing things.
Exactly. Agent systems are kind of the peak of Gen AI application design right now. The LLM shifts roles here. It's less of an answer generator and more of a reasoning engine. It
Mhm.
looks at the user's request and then autonomously figures out the sequence of actions and the resources, the tools it needs to complete a complex, maybe multi-step task that it couldn't possibly do in just one go.
A reasoning engine that uses tools. Okay, walk us through the typical workflow for an agent. I think I saw it described as plan, act, reflect.
That's the core loop. It starts with the plan phase. The agent examines the user's query. Maybe it's what's the current inventory level for product X and what was its sales trend last quarter. It checks that against the list of available tools, it has access to maybe a database query tool, maybe an API analysis tool. Then it formulates a logical step-by-step plan. Step 1, query inventory database for product X. Step 2, query sales database for Q4 trend. Step 3, synthesize results.
Okay, so it makes a plan, then it acts.
Then comes the act-react phase. The agent executes the steps in its plan. It actually calls the necessary tools, runs the database query, calls an external API, maybe executes a Python script. It gets the results back from those actions.
And then reflect what happens there.
This is crucial. After getting a result, it enters the reflect stage. The agent looks at the outcome of its action. Did querying the inventory give me the number I needed? Did the API call return the sales data? It checks if the results move it closer to answering the original overall user question. This reflection might lead it to adjust the plan, maybe realize it needs to call another tool, or decide it now has enough information. It loops through plan, act, reflect until the original goal is achieved. Only then does it assemble and deliver the final synthesized response to the user.
Fascinating. So the tools are absolutely essential. They're the agent's connection to the outside world, its way to actually do stuff.
Yeah.
What kind of capabilities can these tools give an agent?
They are literally its hands and eyes, its external interfaces. Tools can be almost anything the agent needs to execute its plan. Commonly, you see external APIs, maybe for talking to a payment system, a CRM, a travel booking service. They can be databases, allowing the agent to run specific queries against, say, product catalogs or financial records.
Or even code?
Yeah, or they can be specialized code snippets or scripts. Maybe a script for scraping data from a website in real time, or performing some complex calculation locally that the LLM itself can't handle. Without access to these tools, the agent is just a thinker, a planner with no ability to act on the world.
And I heard you can even layer this, creating multi-agent systems. That sounds like setting up an AI department with different specialists.
That's a really good analogy, actually. And yes, these are typically implemented using more advanced frameworks. Instead of having one single agent trying to do everything, you might create several specialized agents. Perhaps you have an inventory query agent, a sales reporting agent, and maybe a customer communication agent.
Okay, so specialized roles.
Right. And then you often have a higher level supervisor agent. This supervisor acts like a manager. It receives the complex user request, breaks it down, and decides which specialized agent is best equipped to handle each part of the task. It routes the subtasks, coordinates the workflow, manages dependencies between the agents, and might even have to reconcile conflicting information if two agents provide different results.
Oh, okay, so that allows for handling really complex enterprise-level requests efficiently by dividing the labor among specialized AI agents.
Exactly. It enables parallel processing and leverages specialized expertise, just like a human team.
Okay, so we've got the core patterns: simple prompting, knowledge-grounded R, and action-oriented agents. That defines how the application thinks and gets information. But having a smart pattern isn't enough. You need a solid process to get from a cool idea to a real, working, scaled application. This is where we get into the full developer journey, what's often called MLOps.
Right. And this is where the rubber really meets the road, where things get serious in terms of resources and risk management.
Yeah, this part seems really interesting because it's about making it real and keeping it running reliably.
And it reflects the industry maturing. We're seeing that massive shift from just using AI tools to actively building Gen AI applications. You mentioned Gartner earlier. They're projecting something like 80% of companies will be using Gen AI in some capacity by 2026. That kind of adoption requires a disciplined, structured approach, starting way back at strategy and going all the way to continuous production monitoring.
Okay, let's break down that journey. Phase 1, strategy and experimentation. Before you even write code for orchestration, you have to pick the right model. Where does a developer even start that research? It feels like there are hundreds of models now.
It starts with doing your homework, really. Meticulous research and evaluation. You can't just grab the biggest, most famous model and assume it's best. Different use cases need different models. Sometimes, believe it or not, a smaller model is actually better.
Better how?
Better performance on a specific task, lower latency, cheaper to run. Developers need to benchmark. They look at performance metrics, model size, how well it's suited for their specific domain like finance or healthcare. They check out places like Hugging Face, these open repositories, compare the stats, and crucially, they often need to test how fast the model responds to latency on the kind of hardware they actually plan to use.
Makes sense. Test before you commit. Beyond just performance, what are the big strategic infrastructure choices developers wrestle with early on?
There are two huge ones that really impact cost and security right from the start. First, self-hosting versus using a cloud service API. Cloud APIs are easy to start with, for sure. But a lot of analyses and what we see in practice suggests that if a company already has the necessary servers and GPUs, self-hosting an LLM can be significantly more cost-effective in the long run.
Especially for high-volume use.
Especially then, yeah.
Yeah.
Those per ATI call costs add up incredibly fast if you have a popular application. Self-hosting gives you predictable costs, usually lower at scale.
Okay, cost is one factor. What's the other big decision?
The other is the trade-off between small language models, SLMs, and large language models, LLMs. This is a really important distinction.
SLM versus LLM. So not just size, but capability focus.
Exactly. Think of it like a massive Swiss Army knife versus a specialized surgeon's scalpel. LLMs are the Swiss Army knives. They can do a bit of everything reasonably well. SLMs are the scalpels. They're intentionally limited in scope, but highly optimized for specific narrow tasks, maybe just classifying emails or extracting specific fields from invoices.
And for those narrow tasks?
For those targeted jobs, SLMs often deliver superior performance, higher accuracy for that specific task, and critically, much lower latency, faster responses. Plus, they need less computational power, so they're cheaper to run. Developers have to weigh that. Do I need the general smarts of a huge LLM, or do I need extreme efficiency and speed for this one core business function? If speed is paramount, an SLM often wins.
Interesting trade-off. Okay, model chosen. Now we get into actually talking to it effectively. Prompt engineering. We touched on system instructions earlier, but what are the more advanced techniques developers use to really steer the model's output?
Right. The goal here is maximizing accuracy, making sure the output is consistent, and that it follows all the rules. We often classify the techniques based on how much help or context we give the model about the kind of answer we want. The simplest is zero-shot prompting.
Zero shot, meaning no examples.
Exactly. You just give the model the task description and the system instructions and hope its baseline training is good enough. Translate the sentence, summarize this text, no examples provided.
Relies purely on its prior knowledge. Okay, what's next?
Then you move up to few-shot prompting. And this is often really effective. Here, before you ask the actual question, you provide the model with, say, 2, 3, maybe 5 examples of the kind of input and the desired output format.
Like showing it what good looks like.
Precisely. You demonstrate the tone you want, the structure, maybe specific formatting conventions. This guidance significantly improves the quality and consistency of the output because the model learns the pattern from the examples you provided.
Okay, that makes sense. And there's one more technique that seems crucial for complex tasks, forcing the model to show its work. Chain of thought. COT.
Chain of thought, COT, is vital for anything involving complex reasoning. Think financial analysis, debugging code, multi-step problem solving. With COT, you explicitly instruct the model in the prompt. Explain your reasoning step by step before giving the final answer.
So it has to think out loud, essentially.
Yes. It forces the model to break the problem down into smaller logical steps and articulate its deduction path. This drastically reduces the chance of it jumping to a wrong conclusion in a complex process. And just as importantly, it makes the whole thing transparent. If the model does get it wrong, you can see exactly where its reasoning went off track, which makes debugging and auditing possible.
That's huge for trust and reliability. Okay, so we have the model, we have prompting strategies. Now the massive question, how do we get our company's own private, proprietary data into the mix? This seems to be where ag versus fine-tuning comes in, and it causes a lot of confusion.
It's probably the single biggest strategic decision around data integration, yeah. And understanding the trade-offs is key. Let's recap RAG first. As we said, RAG uses a pre-trained base model. You don't change the model itself. Instead, you augment it at runtime during the request by retrieving relevant context from that external vector database.
Right, giving it the specific facts it needs for that one question.
Exactly. The result is highly precise, up-to-date answers grounded in your data without ever modifying the core LLM.
What are the big advantages of taking the ARGIS approach?
The main ones are speed of iteration and data freshness. You can add a new document to your vector store, and seconds later, the RG system can use that information in its answers. That's impossible with other methods. It's crucial for anything needing real-time context, inventory checks, news analysis, support tickets.
And probably cheaper and safer.
Generally, yes. Cheaper because you avoid the significant costs of retraining the model, and often considered safer because your proprietary data isn't being shipped off to potentially become part of the model's training data. It only exists within the temporary context window of a specific request.
Okay, that's RAG. Now contrast that with fine-tuning. What's happening there?
Fine-tuning is fundamentally different. Here, you are modifying the base model. You take a pre-trained model and you continue training it, but this time using your own curated data set. You're systematically baking your domain-specific knowledge, or maybe specific desired behaviors, or even a particular writing style, directly into the model's internal weights.
But the knowledge becomes part of the model itself.
Exactly. The big advantage is that information is then available for every single request, every inference, without needing that extra retrieval step. This can sometimes lead to lower latency if the RA retrieval step itself was becoming a bottleneck.
But there must be downsides to fine-tuning.
Oh, definitely. First, it's expensive. You need significant compute resources and expertise for the training process. Second, the iteration cycle is much slower. You make changes, then you have to wait hours or days for the model to retrain before you can test it. Our RAG updates are near instantaneous.
And potential risks.
There's the risk of model drift. The model's overall performance on general tasks might degrade after being fine-tuned too heavily on narrow data. And there's the data security aspect. You're typically sending your proprietary data to the model provider or managing a complex internal training process, which carries inherent risks.
Okay, so it's a clear trade-off. If my data changes constantly and I need the latest info, RAG seems better, safer, faster to update.
Generally, yes.
But if I need the model to consistently adopt a very specific corporate personality or writing style in every single response, fine-tuning might be the way to embed that behavior deeply.
That's a good summary of the strategic choice developers have to make. RAG for knowledge injection and freshness, fine-tuning more for embedding specific behaviors or styles.
All right. So model, prompting, data strategy check. Now we move into the actual building and running phases, phase 2 and 3, development, deployment, MLOps. I noticed the source materials really emphasized local model serving during development. Why is running the model on your own machine so important early on?
It's all about speed and security during that intense development phase. It dramatically speeds up what developers call the inner loop, that cycle of write code, test it, find a bug, fix it, test again.
How does local serving help that loop?
By running the LLM locally, maybe on their powerful workstation or an on-premise server, developers can send test requests directly to the model's API, maybe via localhost. They completely bypass internet latency, avoid waiting for cloud services, and aren't hitting API rate limits or paying for every single test call. This makes iteration incredibly fast.
And the security angle.
Plus, especially if you're working with sensitive internal data, running the model locally keeps all that data securely on-premise throughout the entire development cycle. It never leaves your controlled environment, which is often a critical requirement for compliance.
Makes sense. Faster loops, tighter security. And developers aren't usually building these complex RA or agent flows from scratch, right? They lean on frameworks.
Oh, absolutely. Trying to manage all those chained calls, tool interactions, and context stuffing manually would be a nightmare. Frameworks, like the popular LangChain, for instance, are essential. They abstract away all the low-level complexity, handling the different API formats for various model providers, managing conversation memory, structuring the RA retrieval.
So the framework handles the plumbing.
Pretty much. This abstraction lets developers focus on the actual application logic and features designing the complex workflows, like chaining multiple model calls together, maybe using the output of one call to decide which tool to use next, implementing that conditional logic rather than getting bogged down writing boilerplate code just to talk to the model.
Okay, so development speeds up. Now the final hurdle, getting it into production reliably and keeping it there. MLOps. This sounds like DevOps, but for machine learning. What kind of specialized infrastructure do you need for Gen AI at scale? or beyond just running a web server here?
Yeah, you're dealing with fundamentally different compute needs, mainly driven by GPUs, which are expensive and need careful management. To deploy efficiently, handle fluctuating traffic, and make sure you're getting the most out of those pricey GPUs, containerization using tools like Docker and orchestration platforms, with Kubernetes being the dominant one, are pretty much standard practice.
Why Kubernetes specifically?
Kubernetes is brilliant at managing containerized applications at scale. It can automatically scale the number of application instances up or down based on user demand, ensuring responsiveness. Crucially for AI, it also manages the complex task of scheduling workloads onto servers with available GPUs and load balancing requests across them efficiently. Without that kind of orchestration, scaling reliably is incredibly difficult.
Okay, containers and orchestration handle the scaling. You also mentioned specialized runtimes like VLLM. What do they do?
Right, so standard web servers aren't really optimized for the unique demands of serving large language models. Specialized model serving runtimes, like VLLM or others, are built specifically for high throughput, low latency inference. They use clever techniques under the hood, things like continuous batching and page attention, that basically allow the GPU hardware to process incoming requests much more efficiently and in parallel than a generic server could.
So faster responses for users, lower costs for the provider.
Exactly. Especially when you have many users hitting the service at the same time. These runtimes are common practice in serious production deployment.
And we know companies rarely bet on just one horse. They usually mix and match solutions, right? A hybrid approach.
That's definitely the reality we see. Most organizations end up using a kind of multi-model strategy, like that Swiss Army knife idea again. They'll use different models, maybe some SLMs for specific tasks, a big LLM for general chat, perhaps a mix of open source and proprietary models depending on the use case.
And deploy them in different places.
Yeah, and they'll often deploy these using a hybrid infrastructure. Maybe they run sensitive tasks or specialized SLMs on their own on-premise hardware for security and control, but use cloud resources for the big general LLMs or to handle sudden bursts in traffic. This mix and match approach lets them optimize for cost, performance, and security all at once.
Okay, finally, the ops part of MLOps, continuous monitoring.
Yeah.
How is monitoring an AI application different from monitoring a traditional website or database?
The core principles are similar. You still need to watch uptime, latency, errors. But with AI, the focus has to expand significantly. You're not just monitoring if the application is running, you have to continuously monitor the behavior and quality of the model's output.
Behavior. Like, is it still giving good answers?
Precisely. This means setting up structured benchmarking, regularly feeding the model test prompts and checking if its accuracy, its compliance with instructions, its tone, its consistency are all still meeting the required standards. It also means having robust exception handling specifically for model failures. What do you do if the model hallucinates or gives a biased answer or refuses to answer appropriately? MLOps for AI is about ensuring the model remains effective, safe, and aligned with business goals throughout its entire time in production. It's an ongoing process. Okay, so if we tie all these pieces together, the patterns like RAG and agents, the whole MLOps pipeline we just discussed, and ask where they're making the biggest, most immediate difference in the business world right now. Two areas really jump out in the sources. First, tackling that mountain of technical debt and legacy systems. Second, automating really complex cognitive document processing tasks.
Let's start with the legacy debt, specifically those old COBOL systems.
Yeah.
You find these running the absolute core logic in huge organizations like banks, insurance companies. They're critical, but they're often described as these giant, tangled monoliths. Why are they such a notorious challenge to modernize?
Oh, the challenge is immense. You're often talking about systems with literally tens of thousands of individual COBOL program files written decades ago, handling absolutely mission-critical stuff like calculating interest or processing claims. The core problems are just brutal. First, the sheer complexity and size makes any change incredibly risky and time-consuming.
And nobody understands them anymore.
That's the second huge issue, a profound lack of transparency. The original developers are long gone, documentation is often missing, outdated, or just plain wrong. So current engineers have an incredibly hard time figuring out which specific piece of this ancient code actually handles, say, customer address changes. This makes debugging a nightmare and introduces massive risk every single time someone tries to modify anything.
Okay, so it's this opaque, critical black box. How does an LLM help here? It's not like the LLM can just rewrite the whole thing overnight.
No, definitely not a rewrite. The LLM acts more like a superpowered analysis and refactoring assistant, specifically one that's been trained heavily on COBOL code and documentation patterns. Its first and maybe most critical contribution is automated documentation.
It reads the code and writes the manual.
Essentially, yes. An LLM trained on COBOL can analyze that entire sprawling application, all those thousands of files, and generate comprehensive modern documentation. It can map out the data flows, identify program dependencies, explain what different modules are supposed to do based on the code. This immediately creates that high-level understanding, that map of the system that was missing for decades. It tackles the transparency problem head-on.
That alone sounds incredibly valuable, like finally getting a blueprint for the old house.
It's the foundation for everything else. Then its second key ability is refactoring support. Once the LLM understands the code's structure from that analysis phase, it can actively help the human maintenance teams. It can identify logically related chunks of code scattered across multiple files. For instance, it might say, hey, these 57 routines, these data structures, and these specific procedural calls all seem to relate to policy endorsement processing.
Ah, so it finds the natural seams, the parts that could potentially be broken off.
Exactly. It identifies these logical units that represent distinct business functions, which are the prime candidates for extraction.
Okay, so this isn't a big bang replacement. It's more of a gradual, safer, iterative modernization process. Can you walk us through how that transformation from monolith to something more modern, maybe service-oriented, unfolds using the LLM assistant?
It's designed to be low risk and incremental. Step one, as we said, is that full analysis and documentation generation by the LLM. Get the map. Step two is using that map, combined with the current business expert's knowledge, to pinpoint a specific, well-defined functional unit you want to modernize. First, let's say, the custom adjust update function.
Okay, identify the target, then use the LLM to cut it out.
Step three is the assisted extraction and refactoring. The LLM helps the developers carefully pull out all the relevant code snippets identified in Step 2. It might even suggest how to rewrite some archaic COBOL logic into more modern modular functions. This extracted code then gets refactored into a completely independent, self-contained service, maybe written in a modern language like Java or Python with its own clean API interface.
So you carve off a piece and make it a standalone service. Then what?
Step 4 is the iterative integration. You modify the remaining COBOL monolith slightly. Instead of executing its old internal address update code, it now makes a simple API call to the new external address update service whenever it needs that function performed. You rinse and repeat this process, analyze, identify, extract, integrate potentially hundreds or thousands of times, systematically breaking down the monolith piece by piece into manageable modern services.
Wow. The business value there seems huge. You get improved maintainability because the services are smaller and use modern tools, less risk when making changes, more transparency. And critically, those core business functions, which were locked away inside the COBOL beast, suddenly become accessible via APIs. They can be integrated into new digital products and workflows across the whole company.
Precisely. It turns that suffocating technical debt into reusable, active business capabilities. It transforms a decades-old liability into a modern platform component.
That's a powerful application. Okay, let's switch to the second major use case, automating complex contract analysis. This sounds like it requires a really sophisticated setup, bringing together RA, maybe agents, and this idea of an orchestration hub.
Yeah, this one pushes the boundaries a bit more. Think about traditional contract management. You've got maybe thousands, tens of thousands of contracts sitting in document repositories or specialized systems. When someone needs information like, what are our termination rights under this specific supplier agreement? It usually involves a subject matter expert, an SME, maybe a lawyer, or a procurement specialist.
And they have to manually find it.
Right. They have to manually search the system, retrieve the right document, often read through dozens or hundreds of pages, mentally compare clauses, and perform this complex cognitive analysis just to extract the key facts or figure out the next best action required. It's incredibly slow, very expensive because SME time is valuable, and it just doesn't scale. You can't just hire enough experts to read every contract instantly.
Okay, so the manual bottleneck is the SME's cognitive processing time. The goal here is to automate that understanding. Make the system grasp the content of the documents as soon as they arrive, freeing up the SME for higher value work.
Exactly. Maximize the expert's efficiency by having the system do the heavy lifting of understanding.
What does the architecture for something like this look like? You mentioned an orchestration hub.
So the existing systems, your content management system, your contract lifecycle management tool, they often within the system of record. They still hold the official documents. But you augment them with two key new components, the generative AI capabilities, and critically, the central orchestration hub. Think of the hub as the conductor of the orchestra, the central coordinator managing the entire complex workflow and talking to all the different pieces.
Okay, the hub is the brain. Walk us through its process flow, starting with getting the data ready. How do you prepare dense legal contracts for this kind of high-stakes automated analysis?
It starts, again, with a robust ingestion and vectorization pipeline, but with a twist. A crawler goes through the existing systems, reads the contract documents, even pulling text from scanned images or weird formats using OCR. The extracted text is then passed to an initial AI model. Now, this model does more than just create a vector embedding of the raw text.
What else does it do?
Crucially, it performs semantic analysis to identify and tag common functional sections within the contract. It learns to recognize things like the governing law section, the indemnification clause, the force majeure provisions, the limitation of liability part. It then creates specific, structured, contextual metadata tags for each identified section. Both the raw text chunks and these vital metadata tags get stored together in the vector store.
Okay, wait. This metadata tagging by AI seems really important. Why is it so much better than just doing a standard semantic vector search on the contract text itself?
This is a key differentiator. Standard semantic search is good at finding text that means similar things or uses similar words. But in legal contracts, you often have clauses that have the exact same legal effect or functional purpose, but are worded completely differently. Maybe one uses UK legal phrasing, another uses US phrasing for the same concept.
Ah, so semantic search might miss the connection because the words are too different.
Exactly. They might be semantically distant even though they serve the same function. Standard vector search might fail to pull up both relevant clauses if you're trying to compare, say, all your force majeure clauses across different templates. The AI-generated contextual metadata solves this context problem. The system knows, because of the tag, this chunk of text is a force majeure clause, regardless of the specific wording used. This makes retrieval based on functional intent incredibly precise and enables reliable comparison across documents.
That's clever. It finds things based on legal function, not just words. Huge improvement for accuracy. Okay, so data's ingested and tagged. Step 2 is the user interaction.
Right. The SME, the user, interacts typically through a conversational interface. They chat with the orchestration hub. The hub acts like that supervisor agent we talked about, interpreting the request and directing traffic. The user might ask something complex like, show me all the client contracts we signed in the last 6 months that have a limitation of liability cap below $1 million and compare those clauses to our standard template.
Okay, a complex multi-part query, which then triggers the RAG process orchestrated by the hub.
Precisely. Step 3 is the retrieval-augmented generation. The hub understands a user wants specific clauses based on criteria, date, type, value, and wants a comparison. It uses those highly accurate AI-generated metadata tags to perform a very fast targeted retrieval from the vector store, pulling back only the relevant limitation of liability clauses from the contracts matching the date and value criteria, plus the standard template clause.
Okay, it gets the right snippets using the tags.
Then it constructs the prompt for the LLM. This prompt includes the retrieved text snippets and gives the LLM a clear instruction, like, compare the following limitation of liability clauses, highlighting any significant deviations from the standard template clause provided. The LLM generates the comparison text.
But the hub's job isn't done just by showing the LLM's text comparison, right? It needs to add more value, maybe suggest an action.
Absolutely critical point. The hub does much more than just pass along the LLM's output. This is step 4, orchestration and integration. The hub takes the LLM's generated text comparison and evaluates it against a layer of predefined internal business rules, BR.
Business rules, like company policies.
Exactly. These are rules codified by the business experts, for example. Rule: if any contract's limitation of liability cap is less than $500,000, it must be flagged for immediate review by the senior legal counsel. The hub applies these rules to the LLM's findings. So it moves beyond just summarizing the difference to providing a direct, actionable recommendation, like alert. Contract #123 contains a non-compliant liability cap $400, requiring immediate legal review according to BR L07.
Wow, okay, so it interprets the LLM output through the lens of company policy.
Yes. And finally, it connects this finding to the wider enterprise context. The hub can integrate with other systems. It might check the CRM system to see the overall value or risk score of the client associated with that contract. It might check the ERP system to see if there are outstanding payments. This provides the full business picture needed to make an informed decision.
And based on all the LAM analysis, the business rule check, the external system content, the hub can then trigger actions.
Correct. Based on that complete picture, the hub can initiate automated real-world actions. It could automatically send a notification email with the relevant details to the designated legal team member, update a status field in the contract management system, or even create a task in a project management tool.
This strategic value there seems enormous. You're talking massive time savings for SMEs, no more manual reading for basic fact extraction or comparison, faster value creation because decisions happen quicker, consistent auditable results based on defined rules, and crucially, scalability. You can suddenly process thousands of contracts with a level of understanding that was previously impossible without hiring an army of experts.
It effectively turns static institutional knowledge locked in documents into dynamic, automated intelligence that drives action.
So, looking back at this whole journey, what does it really mean for you, the listener, the developer, the architect? We've traced this evolution today, right? Starting from just writing a simple instruction in a prompt
Yeah, all the way through needing robust MLOps infrastructure to handle scale.
and culminating in these really complex, multi-layered systems like that orchestration hub, coordinating proprietary data using RAG,
Yeah.
triggering real-world actions using agents, and enforcing critical business logic through rules engines.
It really confirms that AI isn't just an experiment or a cool add-on anymore. It's becoming a core fundamental component of the modern enterprise application stack. And the nature of the challenge for developers has fundamentally shifted.
How so?
We're moving away from the old world of just debugging complex, monolithic code bases. The new challenge is ensuring the behavior of these orchestrated AI systems, these interacting agents in our RAG pipelines, is continuously monitored, validated, benchmarked, and kept tightly aligned with those crucial business rules and safety guardrails. It's about managing emergent behavior as much as fixing bugs.
That's a really insightful point, managing the behavior, not just the code. And thinking back to our MLOps discussion, the sources pointed out that those specialized small language models, the SLMs, often beat the giant LLMs on specific tasks, better performance, lower latency, lower cost.
Right, the scalpel versus the Swiss Army knife again?
So if real-world deployments start prioritizing efficiency, cost, and deep specialization for core tasks over just having one massive generalist model, it raises a really interesting question for the future, doesn't it? Does the future of practical Gen AI development rely less on building ever larger singular models and more on mastering that sophisticated coordination, that orchestration hub pattern, managing potentially dozens of smaller, specialized AI models working together? Something for you to think about or maybe dig into on your own?